We're off to chapter 8 here. Off to chapter 8, which this then should be exam 3 stuff we're off to here, I think. So we're going to talk about atomic masses in this table, in this chapter. We're also going to be talking about percent composition by mass, empirical and molecular formulas. So let's get into it here. So atomic masses are based on obviously the number of protons, electrons, and neutrons there are. Atoms are extremely small, so clearly you can't just kind of pick one up and put it on a balance. And when we talk about atomic masses, we are talking now about a lot of times the number that we see on the bottom of the periodic table there. Those are the atomic masses of all the elements. We will also talk about in this chapter another sort of version of that number, which is sometimes referred to as molar mass, which is just a little bit different in terms of how we use it. So a lot of times in chemistry, when we can't really measure something directly, a lot of times what they will do is pick something to use as a standard. So what they picked for atomic masses was an isotope of carbon, which is the carbon-12 isotope. And the carbon-12 isotope has a mass of exactly 12 AMU. AMU is an atomic mass unit. It is a unit that, frankly, we don't use all that much. We do use it when we talk about atomic mass. We don't use it a lot in the calculations. As we'll talk about in this chapter, and as I mentioned a second ago, we use kind of a more commonly used unit, which is molar mass, which is more applicable in our situations because it deals with grams rather than AMU. But we'll talk about that in just a bit. So basically, they used the carbon-12 isotope, which has 6 protons and 6 neutrons. And they sort of measured everybody in comparison to that carbon-12 isotope and said, like, hydrogen's only about 8% as big as the carbon-12 isotope. So they did a bunch of calculations to come up with really the atomic masses that we kind of see on the periodic table. So for example, as I just mentioned, something like hydrogen is about 8.4% as massive as carbon-12, and that is 8.4% converted into a decimal times 12. Gives us a atomic mass for something like hydrogen of 1.008 AMU, which is kind of what we see on the periodic table when we look at it. We can find other atomic masses, obviously, from the periodic table, and one sort of conversion that we use for that is, for example, hydrogen 1.008. What we could say is there are 1.008 AMU in an atom of hydrogen. So that is sort of one way that you could kind of pull the numbers off the periodic table. In general, when we use atomic mass and later when we use molar mass, the typical rule is about 4 significant figures is usually what you pull from the periodic table. Depending on your periodic table, it may have a lot of numbers underneath each of the elements, or maybe not so much. But usually for calculations, if you go to the periodic table and pull off that atomic mass, or again, the molar mass later on, we do use it, and usually about 4 significant figures. So when we look at something like carbon, for example, what we actually see underneath carbon is actually 12.01, which means it is 12.01 AMU per atom. And you might say to yourself, well, if carbon was used as sort of the standard isotope and it had a mass of 12, why do we see sort of 12.01 when we look under the carbon? And the reason that we do see that is what we are actually looking at when we look at the periodic table is what is sometimes referred to as the average atomic masses, although most people don't call it that, they just call it atomic masses. But what it is an average of all the naturally occurring isotopes for that particular element. So every element will have a certain number of naturally occurring isotopes, and sort of the combination of all their masses together is how we get those up on the periodic table. There's actually sort of a formula that you can use to calculate atomic mass using AMU. And if you wanted to calculate the atomic mass of an element in AMU. You basically take the percent abundance is sometimes referred to of the first isotope, and you times it by the atomic mass of the first isotope. And then what you do is actually add it. So not multiply or anything like that. You actually would add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And then basically you would continue that pattern depending on how many naturally occurring isotopes. So a lot of times you may be given like, hey, this isotope has a relative abundance of 22%. The other one has a relative abundance of 70 some odd percent. And when we add up the percent abundance or relative abundance is sometimes referred to, the percentages should add up to 100%. That means you have all the naturally occurring isotopes. If you add up the percentages and they don't equal 100%, then you are missing an isotope somewhere along the way. So this is the way that we sort of calculate the atomic masses that we see on the periodic table, once again, based on all those naturally occurring isotopes. So if we look at carbon, for example, carbon really has kind of two isotopes. It has kind of carbon-12 isotope and the carbon-13 isotope. And the carbon-12 isotope occurs about 99% of the time. The carbon-13 is about 1% of the time. And if we wanted to calculate the atomic mass of carbon, we would use these numbers. By the way, we would just quickly look at the percentages, and they do add up to about 100%. So we know we got pretty much all the naturally occurring isotopes. In this case, we would take the first isotope, which is our carbon-12, and we would convert it into a decimal, the percentage. You could do that by moving the decimal place 2 places to the left, or divide it by 100, which will move it for you 2 places to the left. We times it by the atomic mass of the carbon-12 isotope, which is 12. We then again add it to the percentage of the carbon-13 isotope, which is the 1.1% converted into a decimal, times the atomic mass of our carbon-13. And if we do that, we will get something like 12.01 AMU, which is what we do see underneath carbon. It's really a combination of both the carbon-12 isotope and the carbon-13's isotope's mass, and we kind of use that average mass of both of those as the atomic mass for carbon. Question on that calculation there. It is important to remember that these are really just average values, which means that if you could like pick up a carbon sort of atom, if you will, and put it on a balance, you will never find one that has an atomic mass of 12.01. You would either find one that is a carbon-12 isotope that has a atomic mass of carbon-12, or you would find one that is the carbon-13 isotope that has the mass of carbon-13. Any questions on that there? There we go. So how can we figure out the sort of percentages of each of these isotopes and maybe their relative masses? One of the techniques that's used to do this is what's referred to as mass spec or mass spectrometry. And basically it is atoms that are ionized, sent down tubes where there's an electrical field and a magnetic field. And basically that's able to sort of separate out the different isotopes based on their masses, and you'll also see basically different peaks or different heights of the peaks, which will give you kind of the percentages of each of those guys, of those isotopes that are present. And this is a typical sort of mass spec chart that you get out. These are our relative isotopes and our relative masses. And again, our relative percentages here. So roughly 75-ish, 25-ish sort of percent, around 100% of those chlorine isotopes coming out. So that is sort of how you can kind of figure out those percentages of those isotopes, and also, you know, the relative masses as they move down the graph. They'll be a little bit slower and sort of move off to the left, the lighter ones. So as the sample goes through, you heat it up really and ionize it, goes through first an electrical field, and as we talked about when we were talking about the atom, obviously we can use the electrical field and a magnetic field to separate out things that have sort of charges. And as they come through here, they go through the magnet. And again, on the graph, kind of our heaviest guys end up to the right here on the detector, and our light guys kind of go there to the left. And again, that will sort of separate them out by the mass. And again, the relative sort of peaks that you see on the graph, again, will give you sort of your percentages that occur. So why don't you try this one? If copper is 69.17%, copper 63, and has a mass of 62.9396, and copper 65 has a mass of 64.9278. Okay, let's take a look. So we're given two isotopes of copper. So we have copper 63. And it occurs 69.17% of the time, and it has a mass of 62.9396 AMU. We also have copper 65 here that has a mass of 64.9278 AMU. Once again, here they did not give us that percentage of our copper 65, assuming probably correctly here in this case that there's just these two isotopes, so all the naturally occurring ones. We could get the percentage of our copper 65 by subtracting from 100%, right? So take 100% minus 69.17% gets us about 30.83%, which would be our missing percentage that we need for the calculation. Any questions on that? Now that we have really the percentage and the mass of each of these isotopes, we could go into our formula. So our atomic mass will equal our first isotope. I'm just going to move the decimal place 2 places to the left. So it's going to give me 0.6917% basically. We're going to times that by our mass of 62.9396 AMU. We are again going to add it here, not multiply, to our second isotope. Also, I'm going to move the decimal place 2 places to the left and times it by 64.9278. AMU. That is going to get us here. We got 0.6917 times 62.9396 plus 0.3083 times 64.9278. Going to give us something like 63.55 AMU. Which I think is fairly close to what you see there for copper on the periodic table. Any questions on that calculation there? So again, this is basically the similar calculation as to how we get all those numbers there on the periodic table. Any questions? You try one here, an isotope that was 70.5% abundant with an atomic mass of 117.80. While the other naturally occurring isotope has an abundance of 29.5% and an atomic mass of 120. Calculate the atomic mass of this mystery element here in AMU. So see what you come up with. All right, let's take a look. So again, a couple things we want to look at, which is first off, we have the percent abundance of these two isotopes. We just want to quickly take a look at the percentages. And they do add up to about 100% there, so that is good. Again, if they didn't, you would definitely be probably missing something, and you would have some other way to do it. By the way, if we were missing a percentage and we had the other percentages, we could add up the percentages, right, and subtract from 100, right? And that will tell us, you know, what the missing percentage would be. So we're going to figure out the atomic mass here by taking the first isotope, which is this guy. I'm going to convert it into a decimal. So we're going to move the decimal place 2 places to the left, or again, you can divide by 100 to do that. We're going to times it by the atomic mass of the first isotope. We're then going to do the same thing for the second percentage. We're going to divide it by 100 or move the decimal place, and that will get us 0.295 times our second isotope's mass, 120.85. And if we do all that good stuff there, about 118.7 AMU in this case, yeah. Which I made it up, but if we look on the periodic table, it looks like we might be talking about 10 there. Yeah, that's 118.7. Bless you. Any questions on that calculation there? So again, this is essentially how we do the calculation to figure out the atomic masses that we do see on the periodic table. Okay. So atoms are very tiny masses. So atomic mass unit and its equivalent form to a gram, as you can see, is 1.66 times 10 to the minus 24 grams. So 1 AMU is a very small amount of grams. All right, so we talked about that. So we can do and use atomic masses in AMU as conversion factors. And as I said, we probably won't do a lot of this, and you really don't do a lot of it in chemistry too much using the AMU sort of version. But again, if we were going to try to figure out the mass in AMU of 431 atoms of carbon, we would use our atomic mass from the periodic table as a conversion factor. So we could say there are 12.01 AMUs in an atom of carbon, or we could say in an atom of carbon, there are 12.01 AMU. So we really could use it as a conversion factor, and that's what we did here. We took the 431 carbon atoms, we put atoms of carbon on the bottom so they cancel. We basically multiplied the top, and we end up with 5176 AMU would be the mass there of 431 carbons. And obviously you could use the conversion on the other page if you want to know how many grams that was, kind of going a long way around it to figure it out. Another one here, if we look at aluminum, and if we look underneath aluminum on the periodic table, it will say 2698. So once again, one version of that, we could say 2698 AMU in an atom. Or an atom is 26.98 AMU. So once again, using that as a conversion factor here, the atoms of aluminum will cancel. Multiplying our 75 times our 2698 ends up with 2024 AMU. This is similar to how we do calculations, but we do use molar mass, which we're going to talk about here in just a second. And molar mass is numerically equivalent to what we see on the periodic table for atomic mass. It just has different units of grams per mole, which makes it a little bit more useful for us, because a lot of times when we do go to weigh something out, it's in the units of grams. So a lot of times when we do calculations, molar mass is really kind of the version that we use from the periodic table rather than AMU, which, you know, if you go to a scale, it doesn't really say AMU on it, but it does say grams. Any questions on AMU per atom conversions there? Okay. All right, here. Let's see. Maybe I could get it to go. Let's see. All right, so let's talk a little bit more about some useful sort of conversions, and that is molar mass and Avogadro's number. So we'll start with Avogadro's number and the mole. So in chemistry, we do have a sort of value that we use a lot, which is a mole. And the abbreviation of a mole is MOL, as you can see there in the middle. It had abbreviated some way, so they got rid of the E. It is important, though, that when people see that MOL abbreviation, sometimes a lot of people jump to the conclusion that it is molecules, but it is not molecules. It is moles. So that's a very common sort of mistake that people make. They see the MOL and think molecules rather than moles. So keep that in mind as you go through it. But what does a mole represent? A mole represents really a certain amount of something. So in life, we have a lot of words that mean a actual number. If we have a pair of something, right, that means that you have 2. If you have a dozen of something, that means you have 12. If you're old and you have a gross of pencils. That's how they used to call them. It's 144 is what a gross represents. So we do have these names that sort of represent a numerical value. And in chemistry, the mole is really that sort of name that we use. And 1 mole of anything will equal 6.022 times 10 to the 23, which is known as Avogadro's number. And as we will see, the units of Avogadro's number are different and can be different. We could have them being atoms, which is a common unit. They could be molecules. They could be particles. They could be pizzas. They could be shoes, whatever it may be. Although you do come across the occasional pizza in chemistry, but most of the time it is going to be atoms and molecules, which are the most common units that we associate with Avogadro's number. So 1 mole of anything, just like a dozen of something represents 12, a mole of something in chemistry represents 6.022 times 10 to the 23. Which, as I mentioned, is pretty much Avogadro's number here. And we use Avogadro's number really as a conversion factor. We use it to convert between moles and atoms or moles and molecules. So very commonly, we use this as a conversion factor to go between moles to atoms or molecules. And backwards. And we could use it as a conversion factor like so. Obviously, if you have moles, you would multiply by Avogadro's number. And that would give you atoms. And if you had atoms or molecules, you would divide by Avogadro's number. And that will get you moles. So 1 mole of hydrogen would have 6.022 times 10 to the 23 atoms of hydrogen. 1 mole of carbon would have 6.022 times 10 to the 23 atoms of carbon. 1 mole of water would have 6.022 times 10 to the 23 molecules of water. We use molecules for water because it is a molecule, but for any individual element, we use atoms typically. So again, that's why those units kind of change, but it is the same number. And for any of those relationships, we could write 2 conversion factors. Once again, we could say 1 mole of hydrogen, 6.022 times 10 to the 23 atoms. And we could reverse it, 6.022 times 10 to the 23 atoms of hydrogen would give us 1 mole of hydrogen. So any of those relationships you could use Avogadro's number with. Anybody from the periodic table by itself, any element, which then it would be atoms for Avogadro's numbers units. And you can use it for any molecule or compound, and it would be molecules as the units that you would use. Now, sometimes people go crazy with Avogadro's number. They want to use it in every calculation because, well, frankly, you remember that number and you feel like you should use it in every calculation because it makes it more chemistry-like, I suppose, but you should not do that. So you really should only use Avogadro's number if you are given a number that's in atoms or molecules, or you're really asked to calculate something that needs atoms or molecules. So if there's really no mention of atoms or molecules, you should not use Avogadro's number. Any questions on that there? Now, Avogadro's number, like I said, does represent a certain amount, and we use it as a conversion factor. Again, just like a dozen means you have 12 oranges. Now, we just talked about atomic mass and AMU from the periodic table, but really a more convenient sort of unit that we pull from the periodic table, and it really is the same number as we saw with the atomic mass, is what is sometimes referred to as the molar mass. And the molar mass has units of grams per mole. And the molar mass is really how many grams there are per 1 mole of a substance. And numerically speaking, the conversion factor between AMU and atom and grams to moles, it actually comes out to be in the same number that we see on the periodic table. So just like when we went to the periodic table and we saw that there was 1.008 AMU in an atom, we could go to the periodic table and pull that same 1.008 number off underneath hydrogen and say that there are 1.008 grams of hydrogen and 1 mole of hydrogen. That means that basically the molar mass of hydrogen is 1.008 grams per mole. Molar mass is always this way. The number always stays with the grams part, and it's always 1 mole. So number always stays with the grams part, and it's always 1 mole. We could do that from anybody on the periodic table. If we had carbon, there would be 12.01 grams of carbon in 1 mole of carbon, which means the molar mass of carbon, 12.01 grams per mole. We also could do it for things like, say, water, for example, which is not just an element by itself. In 1 mole of water, we basically would have 18.02 grams of water. And we get that by basically adding up all the parts. So water, there are 2 hydrogens, each from the periodic table as 1.008 grams per mole, plus 1 oxygen from the periodic table, that is 16 grams per mole. And that gives us our 18.02 grams per mole as the molar mass of water. So when you go to calculate the molar mass of a molecule or a compound, you basically just go to the periodic table, you add up all the parts that are there, and that would be how many grams there are per 1 mole of that particular substance. Question on that there. We use this like a conversion factor as well. So we could say, again, for water, that there's 18.02 grams per mole for water. Or you could flip it around and do a mole of water would be 18.02 grams. So again, we really use molar mass as a conversion factor, and molar mass is our conversion factor to go between grams to moles and back. So if you got to do that conversion, take something from grams to moles or take something from moles back to grams, periodic table, molar mass is what you want to do. Once again, you usually take 4 significant figures for each element when you're pulling off the numbers. Any questions on that there? Now, we know that there is 1.008 grams of hydrogen in 1 mole of hydrogen. There would be how many hydrogen atoms in 1 mole? It would still be Avogadro's number. So that is how they all tie to each other. Same thing here. There's 18.02 grams of water and 1 mole of water. And 1 mole of water would have how many molecules? Yeah, we still have Avogadro's numbers worth of molecules. So that is the relationship of how all those things sort of tie together. And obviously you can convert from one to the next. Any questions on that there? Molar mass and converting from grams to moles, almost one of the most important calculations that you learn in chemistry. You use it a lot in a lot of different places throughout chemistry. So definitely not like this, it will go away. All right, so that is the relationship there between AMU and grams, in case you're curious. All right, so let's talk about this here. As I mentioned, we have basically kind of 2 conversion factors, Avogadro's number, which is what we use to go from moles to atoms or molecules. And we have our molar mass, which we use to go from grams to moles or moles back to grams. So let's do some here as a practice here. All right, how many moles of helium are there in 5.46 moles of helium. If you look at the periodic table where helium is sitting, it will say 4.003 underneath it. So give it a go, see what you come up with. Okay, let's take a look. So first off, what we want to look at is sort of really the conversion that we're doing. We have grams and we want to end up with moles. So we want to go from grams to moles. So the first thing we want to think about, do we need to use Avogadro's number here? The answer is we do not. There's no mention of atoms, right? There's no mention of molecules. So you do not need Avogadro's number. What we do need and what we use for this conversion to go from grams to moles is the molar mass. And the molar mass, once again, comes from the periodic table. And when we pull that number off the periodic table, it means the molar mass of helium is 4.003 grams per mole, which we could use really as a conversion factor. Again, we could use a showing dimensional analysis, 4.003 grams of helium per mole of helium, or a mole. So we're going to start with our grams, 5.46 grams of helium. We're just going to do a little dimensional analysis here. So we do want to actually take the grams and put them on the bottom so that they cancel. This will give us 4.003 grams per mole of helium. Once again, here the grams will cancel, and that'll leave us with 1.36 moles of helium. Significant figures really based off of the original number there, which was 3 significant figures as well. Question on that calculation. As a calculation, you do a lot. Grams to moles in chemistry for sure. Any questions on it? Okay. So why don't we try this one here? What is the mass in grams of, actually, let's do this one. Let's do one here first. What is the, what is the mass of 32.5 moles of CH4? So carbon is 12.01. Hydrogen is 1.008 there. All right, give it a go, see what you come up with in this case. Okay, let's take a look since we're getting to the end here. So once again, we want to think about our conversion. We want the mass. I guess I should have put grams there. Mass in grams. So we're looking for grams and we are given moles. So once again, we want to go from moles in this case, 2 grams. It is the molar mass from the periodic table that's going to allow us to do that. In this case, though, we do have a molecule here that are a compound. So we basically just add up all the parts to it. So the molar mass of CH4 would be, there's 1 carbon from the periodic table, that's 12.01. There are 4 hydrogens, each from the periodic table is 1.008 grams per mole. And if we add all that together, we get a molar mass for carbon CH4 of 16.04 grams per mole. Remember, we could use that as a conversion factor where the grams are up on top and the moles are on the bottom, or if we need to flip it, moles up on top and grams on the bottom. So we'll start with our 32.5 moles of CH4. We want the moles to cancel, so we do want the moles from our molar mass on the bottom. Grams up on top, remember that the grams stay together with the number. Moles will cancel, and we will end up with about 521 grams of CH4 in this case. Again, really based off of that right there, 3 significant figures. Any questions on that calculation? So these type of calculations going from grams to moles or moles to grams is a very, very common calculation that you need to be able to do a lot. And again, it's the periodic table molar mass that allows us to do. All right, so I think, did we not do this one? We did or did not do this one? I don't think we did this one. So why don't we do this one? What is the mass in grams of one gold atom? The molar mass of gold is 197 grams per mole. Take a look here. So in this case, we're looking for the mass in grams of one gold atom. So the key here is obviously the rest of it may not be given to you, but atom means at some point we should probably use Avogadro's number here. And the pathway here is we'd want to go perhaps from atoms to moles, as Avogadro's number would do that for us. And then from moles to grams using the molar mass. So those are really the two sort of conversion factors and pathways is going to allow us to do that. We would, if it obviously wasn't given to you, which it probably would not, go to the periodic table there and find the molar mass for gold. And obviously we do need to know Avogadro's number, which is our 6.022 times 10 to the 23. So we'll start with the one gold atom. Once again, using Avogadro's number as a conversion factor, that means the atoms need to go on the bottom so they cancel. So at this point, the atoms of gold would cancel. And if we stopped at this point, we would be in moles, which again gets us really to this point of the calculation. So we do need to go to the periodic table. And once again, that is where we find that number of 197. Remember that we do pull about 4 significant figures typically from the periodic table when we use it. And that means that there's 197 grams per mole of gold. Or again, if you needed to use it the opposite way, a mole would have 197 grams. So you could use it really either way. In this case, we actually need the moles on the bottom. So we'll use it in this fashion. And a mole of gold would be 197 grams. The moles of gold would cancel, and that's going to leave us grams, which is good. So basically here we're taking 197 and we're dividing it by Avogadro's number, making sure you use the exponent button. And if you hit the right button would help as well. And we'll get something like 3.271 times 10 to the minus 22 grams in this case. Any questions on that there? In terms of the sig figs, because 1 is technically something you would count, you can pretty much do any sig figs you want. So I went with 4 based on the molar mass that has 4 significant figures. Question on that calculation. All right, so give us a couple minutes there, see what you come up with. All right, let's take a look here. So we're looking for how many atoms there are in 0.551 grams of potassium. So the key word here is atoms. So that does tell us that we should use Avogadro's number here somewhere in this problem. We're at grams. And again, we want to end up at atoms. So as we were just talking about earlier, really the one that sort of ties those together are the moles. So in this case, we want to go from grams to moles, which we hopefully know is our molar mass from the periodic table to do so. Once we're at moles, then we could pull out our Avogadro's number, basically to take it to the end of what we are looking for in this case. So we'll go get our potassium here. And as we talked about, and also a reminder, typically speaking, molar mass, 4 significant figures is what you grab off the periodic table to use in calculations and just in general when you calculate molar mass of anything. So this means that we got basically 39.10 grams per mole for potassium. And we're going to use that really as a conversion factor. So we got 0.551 grams of potassium. Setting up dimensional analysis way, we want to go opposite. So the grams are going to go on the bottom here, so they cancel. The moles of potassium will go up on top. If we stop our calculation right at this point, we are in moles of potassium, which is halfway there. We got to here. So now we need to kind of take it the rest of the way using our Avogadro's number, which again is our 1 mole is 6.022 times 10 to the 23. And in this case, it would be atoms. Here, if you did want to get an answer, you could. I probably, again, would not round too much until the end when you do the next step. But here, I'm just going to continue on with the calculation. So again, the nice thing about setting it up as dimensional analysis, I could clearly see moles are up on top, which I want to get rid of. So I should put moles on the bottom here. And that would mean Avogadro's number should go up on top. Remember, opposites cancel, right? So our moles cancel. And now we're going to multiply across and divide to make sure we use our exponent button. Clear our memory, apparently. Let's try that. 0.551 times 6.022 to 23. I do want to hit equals there at the top when I'm done and divide by 3910 and hit equals. And it looks like we will end up with 8.49 times 10 to the 21 atoms of potassium in this case. 3 significant figures based off of obviously the only number that's in that problem, which is 3. Yeah. Any questions on that one? Okay, so obviously grams per mole, molar mass really important. All right, so why don't you try this one? Let's calculate the number of grams in 15.7 moles of iron. Iron is 5585, I hope, still. Look at the periodic table. Okay, let's take a look. So first off, we want to calculate the number of grams in 15.7 moles of iron. Do I need to use Avogadro's number here? I do not, because there's no mention of molecules or atoms or anything like that. So again, this is really a moles to grams conversion, and that is the molar mass from the periodic table that allows us to do that. When we pull that number off, that is 5585 grams per mole as the molar mass for iron. Gives us really, we could use it as a conversion factor so you can see where the units are so we don't make any calculation errors there. And in this case, we will start with 15.7 moles of iron. We want to get rid of moles, so we're going to use it just like this. We can set it up as dimensional analysis. So again, we can see the units and make sure we're multiplying when we want to, and perhaps divide when we want to. In this case, we're going to multiply, and that's going to get us 15.7 times 5585. Going to get us going to give us 876.845. And these would be grams. Sig fig wise, that's where you want to look. We'll consider this sort of an exact number. So that has 3 sig figs, maybe 877 grams of iron. Yeah, would be a good number to go to. Any questions on that calculation there? Yeah. Let's take a look at one more here to finish it up. How many moles of lithium are there in 77.8 grams of lithium? Again, lithium, in case you don't have periodic table, 6.941 would be the number that you would see there. All right, so to finish this one up here, once again, we really do not need Avogadro's number as there is no mention of molecules or atoms. A reminder that if you were asked this question and it did say MOL, that still is moles, so not molecules, so don't get that confused. So once again, this is going to be a grams to moles situation, which is the molar mass from the periodic table. It's going to allow us to do that, and that would be 6.941 grams per mole. And we will take our 77.8 grams of lithium. We want to go opposite, so grams are going to go on the bottom. Moles will go up on top, and the grams will cancel, so we're going to divide in this case, and that's going to get us 11.2 moles of lithium in this case when you do that. Any questions on that? One last thing about molar mass here to really finish up for today is, a very common mistake that people make sometimes is if they see an equation, and let's just say we had 4 waters, for example, and they wanted to calculate the molar mass for water. They oftentimes will try to take this number into account, and you shouldn't do that. So when you're asked to calculate the molar mass, or you need to calculate the molar mass of something, regardless, even if you have it in an equation and there's multiples of it, the molar mass is always calculated based on just the formula by itself. And that's why the molar mass is grams per 1 mole. So 1 mole of the actual substance. So you should always calculate it. So it would still be 18.02 here. Grams per mole would be the proper molar mass. You don't take that 4 into account. You take it into account when we talk about stoichiometry. Then you take it into account. So let's take a look at this problem here. Good look. Let's go back and look again. There we go. In this case, we want to know how many atoms of hydrogen or hydrogen atoms there are in 72.5 grams of C3H8NO. So clearly one of the keywords here, right, are atoms. So again, we're going to need to use Avogadro's number. But in this particular case, we are not interested in everything there. We're just interested in the hydrogen part of it. So we're not actually interested in the carbons or the oxygens in this particular case. So we do need a way in this calculation to go from really the whole thing to just the hydrogen, which is what we're interested in. And one way that you could do that, and sometimes you're asked to do that, and sometimes you'll need to do that in certain calculations, is to sort of relate each element to the entire thing in the compound or the formula, is you could actually use the formula itself as a conversion factor. So when we look at this formula here, these numbers on the bottom, and obviously if there is no number, it represents 1 in that case. These numbers here on the bottom do represent the moles of each of those elements that are present. And that means that actually from this formula here, we could actually write some conversion factors from it, or qualities. We could say that for every 1 mole of the entire thing, I would get 3 moles of just carbon. And again, that would be the subscript that's on the bottom. And I could say for every 1 mole of the entire thing, I would get myself 8 moles of hydrogen. And I could also have a relationship in 1 mole of the entire thing. That would get me 1 mole of oxygen, which obviously is no number written right there. So we could actually use the formula itself as a conversion factor to go from the whole thing to just whatever element we're interested in. And obviously in this problem here, we are interested in hydrogen. So we would be interested in this relationship here. And that relationship is really a mole to mole relationship, which tells us for sure that we need to get our grams into moles so that everything cancels out. So we do need to go in this case from grams to moles of the whole thing. And then once we have moles of the whole thing, we need to use the actual formula here to go from moles of the whole thing to really just moles of hydrogen. And once we have moles of hydrogen, we need to go to atoms of hydrogen. And we have our normal things here to help us do that. We have our molar mass. We have our actual formula here to do that. And we have our Avogadro's number on the back end of the calculation to allow us to get to where we're looking for. So the first step is we do need to get the molar mass of this compound. And again, as we talked about, you basically just add up all the parts that you got going on there. So from the periodic table, carbon is 12.01. And again, that is the number that we see on the bottom. Just like for hydrogen, we see 1.008. And for our friend oxygen, we see 16, or G. Let's go with more of an O, I guess. All right, so to add up the molar mass of this, we have 3 times our 12.01 grams per mole for our carbon. We're going to add it to 8 times 1.008 grams per mole for our hydrogens. And we'll add it to 16 grams per mole for our lonely oxygen. And now we have 3 times 12.01 plus 8 times 1.008 and a 16. Looks like a 60.09 grams per mole. So now that we have the molar mass of our entire compound here, our C3H8O, we can start the calculation. We're going to start with our 72.5 grams of the entire thing. We're going to use the molar mass of the entire thing to take it from grams to moles. So that would be our 60.09 grams on the bottom. So they cancel. Moles of our entire thing here up on top. Grams cancel. That pretty much takes us to this step right there. At this point, we can now use the formula, bless you, we can now use the formula to go from the whole thing to just hydrogen, which is ultimately where we want to end up. And obviously, we would use this highlighted relationship that we saw earlier, and we can use it as a conversion factor, basically. So we want to get rid of the entire thing, and we can see from our dimensional analysis here, it's up on top. So the entire thing would go on the bottom so that it cancels. And up on top would go 8 moles of hydrogen. That's going to cancel out the moles of the entire thing. And now progressing this way, I am now at moles of hydrogen, which is really good. Obviously, if I wanted moles of hydrogen, I get an answer and put a box on it. But I do want atoms in this case. So now we're going to go from moles to atoms. And again, that's going to be our Avogadro's number to do that. So once again, we want to go opposites to cancel. So moles want to go on the bottom here of hydrogen. And on top would be 6.022 times 10 to the 23. And these would be atoms of hydrogen, as we're just into hydrogen at this point. And that should get us to atoms of hydrogen we're looking for. We're going to multiply across the top there, 72.5 times 8 times Avogadro's number using our exponent button. We're going to hit equals and divide by 60.09. And we will get, looks like 5.81 times 10 to the 24 atoms of hydrogen. It's a lot of hydrogen atoms. Any question on that calculation? Clearly, if we were interested in carbon or oxygen, we could do a similar calculation to figure out how many atoms of carbon or oxygen there was. The difference would be at this point, basically. We would just use the proper relationship for either carbon or oxygen, and everything else would really be the same in this conversion. So this is definitely something that you are sometimes asked to do, and something that we'll see in the calculation coming up that you do need to do in some cases. Sort of have that relationship between sort of the whole compound and each of the elements or moles of each of the elements that are present. Any questions on that there? All right, so let's try a couple more here. What is the moles and how many molecules are there in 23.2 grams of ethanol? And once again, your periodic table, 12.01 for carbon, 1.008 for hydrogen, and oxygen 16. All right, so see what you come up for both of those. While we're at it, why don't we add one more? How many? We'll do how many grams of carbon are there? In the same 23.2 grams. All right, so try all three of those, see what you come up with. Okay, let's take a look and see how we're doing here. So we want moles, molecules, and really just carbon by itself. So really the first two parts are sort of together. We do have grams, and we eventually want to get to molecules, and we do want to stop along the way there with moles. And again, this is our same sort of pathway. We're going to need the molar mass to do so, and we will need Avogadro's number in this case, since we are looking for molecules. So we'll start with the molar mass of this compound, and again, we're going to just add up it all from the periodic table here. So we got 2 carbons, each at 12.01. We got 6 hydrogens, each at 1.008 grams per mole. We also have, in this case, just 1 oxygen here at 16 grams per mole in this particular case. So we're just going to add it together. And if we do that, I want to say 4607, maybe, yeah, something like that. That was good. 4607 grams per mole is our molar mass of C2H6O. Again, we're going to use that as a conversion factor here. So we'll do the first one here, which is 23.2 grams of C2H6O. Again, opposites to cancel, so we need to put the grams on the bottom. Remember that when you do molar mass, the grams always stays with the number always stays with the grams, and it's always per 1 mole there up on top in this particular case. The grams will cancel. So since we do want an answer here, we'll take 23.2 and divide it by 46.07, and that will get us 0.504 moles of our C2H6O. Any questions on that so far? That gets us again up to here in terms of our pathway. So now we can use Avogadro's number there to take it the rest of the way. I'm going to write the rounded number because we did want it as an answer here, but I'm going to actually on my calculator just continue on with the whole number that I got on my calculator. And at this point, we want to take our moles to molecules, which is our Avogadro's number. And we do want moles on the bottom so that they cancel. And up on top would go Avogadro's number. Here they would be molecules, as we're dealing with a molecule in this case. The moles will cancel. And again, I'm using the whole number, not the rounded number, 6.022 to the 23. And gives us roughly here 3.03 times 10 to the 23 molecules of C2H6O. Any question on either of those calculations there? Now, looking at the last one down here, we're interested in not the whole thing, but we are interested in just the carbon part. So this is where, again, we could use the formula to help us out. So from the formula here, we see that for every 1 mole of the entire thing, how many moles of carbon do I get? I get, not everybody at once. I would get 2 moles of carbon. Good answer, because that's a 2 right there, yeah. So we do get 2 moles of carbon. I should write carbon would be even better. There we go. And we can use that obviously as a conversion factor to go from the whole thing to just carbon, which is what we're interested in this case. And we're going to shortcut it because frankly, we have the answer right there for the moles of the whole thing. So no sense redoing the calculation. So again, I'm just going to pick it up with that number, which is our moles of our entire thing. And obviously to get there, you would do the first calculation again. And we're going to use the formula to go from the whole thing. So we want the whole thing on the bottom. And we want just the moles of carbon on top, which is 2 moles of carbon. So using the formula here, that's going to get rid of the whole thing, leave us with carbons. At this point, and once again, if I did want just moles of carbon, I could get the answer and I would be done. But I actually want grams of carbon, which means I need to multiply this by the molar mass of just carbon at this point, right? So we do not want to use the molar mass of the entire thing because we have now just transitioned over to just carbon at this point. And carbon, as we can see from the periodic table here, is 1201. So we'll use that as our last step. Opposites here, moles of carbon on the bottom, 12.01 grams of just carbon up on top. And in this case, we'll go here with the rounded number, 0.504 times 2 times 12.01, going to give us 12.1 grams of carbon in this particular compound. Yeah. about 50% carbon, so that's about right. Yes. Any questions on any of those calculations there? All right, so we're looking for how many grams there are in 1 molecule of, sorry, how many grams are there in 1 molecule of caffeine? That's what I'm trying to spit out there. All right, so some numbers again that we've been using still haven't changed. So we'll pop them up here anyways. We'll do our nitrogen and our oxygen. All right, so in this case, we're just looking for the grams in 1 molecule of caffeine. Look here. So once again, the keyword is molecules, tells us Avogadro's numbers involved. We want to end up at grams. So once again, we got molecules, we got to get to grams, and our moles are in the middle there. So we're going to first Avogadro number it, and then we're going to molar mass it, and then we will be out of stuff to do to it. So since we do need the molar mass at some point in this calculation, I'm going to calculate it up front here. So just going to add up all the parts here. So that's going to be 8 times our carbon's molar mass from the periodic table, plus 10 times our hydrogen's molar mass from the periodic table, plus we got there 4 times our nitrogen's molar mass. And lastly, 2 times our oxygen's molar mass. Good thing there's no more letters. I feel like I'm out of room there. We add all that together, $1.96 maybe, $1.94. 194.2 grams per mole is our molar mass. Any questions on getting the molar mass there? Again, obviously it comes from the periodic table, and it's the bottom number there underneath the element. All right, so we'll start with our 1 molecule of caffeine. This big formula, and 402. Just draw a cup of coffee instead. All right, so we're gonna use our Avogadro's number. In this case, we actually want Avogadro's number on the bottom so that the molecules cancel each other out. So 6.022 times 10 to 23 molecules on the bottom per mole of our caffeine up on top. At this point, the molecules of caffeine will cancel out. I'm in moles, which takes me basically to here. So what's left is, again, using our molar mass. So we just calculated there to go the rest of the way. And dimensional analysis wise, we see moles on top, which means on the bottom should go moles of our caffeine. And up on top should go 194.2 grams. The moles will cancel. That will give us grams. So basically 194.2, I think. Divided by Avogadro's number, basically. Not too bad. And it looks like we will end up with, I'll come down here, 3.225 times 10 to the minus 22 grams of caffeine in this case. And in this case, to answer the question, we went 4 significant figures really based off of the molar mass, because if we had 1 molecule, that'd be kind of like something you would just count, right? So more of an exact number. So you really could give it to as many significant figures as you want at the end of this particular calculation. So I just went with the molar mass for significant figures in this particular case. Any questions on obviously converting grams, moles, grams? Need to know how to do that for sure. The occasional throwing in of Avogadro's number, not so much more used than maybe in this chapter, but definitely grams, moles, we use a lot. Any questions on any of that there? The next thing we're going to talk about are molecular formulas and empirical formulas. So first off, a molecular formula pretty much tells you exactly what's in there, what's in the compound, our molecule. So it tells you exactly how many atoms of each element are present. And a molecule, obviously, as we talked about, is really an arrangement of 2 or more atoms together. compound, once again, is a combination of two or more elements that are together. A chemical formula, as we talked about, basically expresses the elements that are involved. And a reminder again that it is the subscripts, right, that tell us, in this case, as we just saw, how many moles or how many atoms of each element are there. And once again, the subscripts always go to the guy to the left. And if there is no subscript, it's assumed to be 1, right? So a molecular formula, again, tells us exactly what is present. And now molecular formulas can be a variety of ways that they are written. Sometimes molecular formulas will frankly not really give you any information about how everybody's sort of connected. Just basically tells you what's there. And sometimes chemical formulas will give you, or molecular formulas will give you some information about how things are connected to each other. So for example, this guy here is a molecular formula there for acetic acid. This formula also is sometimes written C2H4O2, which is also acetic acid. If you count up basically what is present in both of those formulas, they both have two carbons, 4 hydrogens, and 2 oxygens. The bottom formula or molecular formula pretty much just tells you what elements are involved. The top one here actually gives you some structural information about how things are sort of connected. So if you were to draw this, it looks something like this. And as you can see there, this is CH3. And this part here is the COOH part of it, which is a special organic group, which is known as carboxylic acid. So that molecular formula gives a little bit more information about basically how everybody is connected. And by the way, in case you're curious, it is that hydrogen that makes it an acid. It comes off when it is acting as an acid. And then once again, just kind of tell you what is present. Same thing here with ethanol. These are 2 formulas for ethanol. They both have the exact same number of carbons, hydrogens, oxygens. The bottom one here also gives you an idea as to how it's connected. So, you know, it basically looks something like this. And once again, that sort of bottom formula does give you a lot of that information. This being the CH3. This being the CH2 part. And lastly there, oh, you get it maybe. This guy here being the OH part. So again, sometimes those molecular formulas will give you a lot of information about how it's basically connected. And again, in the basic form, it will tell you exactly what is present. And that is different than the empirical formula. Now, the empirical formula is really the simplest whole number ratio of what is present. So the empirical formula doesn't necessarily always tell you what is present, like the molecular formula, how many of each of the elements are present, but it gives you that simplest whole number ratio of what's present. As we can see here, H2O2 is the molecular formula for hydrogen peroxide. That is 2 hydrogens for every 2 oxygens, which basically if you divide by 2, it's the same as 1 hydrogen for every 1 oxygen, although that looks like a 10, which gives us an empirical formula of HO. If we had something like C2H6 as the molecular formula, we could look at this and see that that is 2 carbons for every 6 hydrogens. Once again, in this case, we could divide everybody by 2, which gives us a ratio of 1 carbon for every 3 hydrogens that are present. And that would give us an empirical formula of CH3 in this particular case. So the empirical formula is always the simplest whole number ratio, and that's important. It does need to be a whole number ratio of what's present. So if you could not reduce down everybody by a common number and still get whole numbers, then you shouldn't do that. So sometimes the molecular formula, say for water, that is 2 hydrogens for every 1 oxygen. In this case, you cannot reduce this down anymore and still get a whole number, which means both the molecular formula and the empirical formula in this case would actually be the same. All ionic compound formulas are empirical formulas because when we put them together, the positive charge and the negative charge, we put them together so they equal 0 in the simplest way possible. So whenever you look at an ionic compounds formula, a metal and a non-metal, cation and anion, they're always really empirical formulas. There's also the molecular formula as well, or a formula unit, I guess, in that case, because it's not really a molecule. But they're really all empirical formulas because you should put them together in that simplest fashion. So molecular formula tells you exactly what's there. Empirical formula tells you the exact sort of ratio of what's present. So once again, here's another example, N2H2, that is 2 nitrogens for every 4 hydrogens, gives us an empirical formula of NH2, in this case by simply reducing everybody down here by 2. Again, only the molecular formula tells us the actual number of atoms. The empirical formula is that simplest chemical formula. They're always written to convert the subscripts of the molecular formula into the smallest whole numbers. A lot of times in the lab, if you're doing an experiment, you are sometimes easy to figure out the empirical formula by simply taking differences in mass swings, and you can calculate the empirical formula pretty easily in the lab. So as I mentioned before, some molecules do have both the empirical formula and the molecular formula being the same. Again, in the case of NH3, that is 1 nitrogen for every 3 hydrogens. No way to reduce that down any further. Same thing with CO2, 1 carbon for every 2 oxygens. That is, again, as simplest as you can get it, and you cannot reduce it down any further. All right, so take a moment here and lay up the empirical formula for each of these. This first one here, we got basically 2 carbons for every 2 hydrogens. You clearly can reduce those guys down by 2, which would basically give you 1 carbon for every 1 hydrogen. So the empirical formula there would be CH. Looking at the second one here, that is 2 iodides for every 5 oxygens. There's no way to divide that out and get a whole number, which obviously a formula needs a whole number for the subscripts, which means the empirical formula would be the same in this case as the molecular formula. Any question on those two? Lastly, here we have glucose, which is 6 carbons for every 12 hydrogens. For every 6 oxygens. You could probably see you can divide everybody here by 6. Gives us 1, gives us 2, gives us 1, which are all whole numbers, which means the empirical formula here would be CH2O in this case. Any questions on that? So this is sort of a simple way that you could calculate the empirical formula if you are given the molecular formula and you want to reduce it down. We're going to talk about in a second here how to calculate it with some other information. But before we do that, let's first talk about another important aspect, which is the percent composition by mass. So we can, and it's not, it should be multiplying there. So we could calculate the percent composition by mass by basically taking to figure out the percent of each element present, we take the mass of the element in that particular formula divided by the molar mass of the formula times 100%. So we could calculate the percent composition of each element in a compound by using the molar mass and really taking the mass of each of the elements that are there. Kind of very similar to how we figured out the percent of water in those hydrates that we did the other day. We took the mass of the water divided by the mass of the entire compound. Here, we're just going to take the mass of each element and divide it by the mass of the entire compound. And obviously, to turn it into a percentage, we want to multiply by 100 in this case. So if we take a look at one here, like our hydrogen peroxide, the first thing that we would want to do is get the molar mass here of the hydrogen peroxide. So we're going to go to the periodic table and add up all the parts. So that is 2 times 1.008 for our hydrogens, plus 2 times 16 for our oxygens. That is going to give us a molar mass here of 2 times 1.008 plus a 3402 grams per mole. So we can now figure out the percentage of each of the elements that are present. So if we did the percentage of hydrogen, in the case here, we have 2 hydrogens at 1.008 grams per mole, divided by the molar mass of the entire compound. And we're going to times it by 100% in this case. And that would give us 2 times 1.008 divided by 34.02 times 100. Going to give us 5.926% hydrogen. Now we'll do the same thing for our oxygen in this case. So the percent of oxygen is in this case 2 times 16 grams per mole, as there's 2 oxygens in that compound divided by the molar mass of the entire compound times 100% in this case. So taking 32 divided by 34.02 gets us about 9406% oxygen. Any questions on that? Yeah. By the way, once I actually have the percentage here of hydrogen, I can figure out the percentage of oxygen by doing what? Yeah, because there's only one other element present. I could take 100 minus that, right? The percentage of hydrogen. You could also get yourself there to the percentage of oxygen, since there's only 2 obviously here as well. And all the percentages obviously should add up to 100% because they're made up of those 2 elements in this case. Any questions on that? Again, with rounding, you might get 9407 or something like that, but pretty close. All right, so let's take a look at the empirical formula here for hydrogen peroxide, which is HO. So why don't you calculate the percent composition of each element here in the empirical formula? All right, so we approach this the same way. We're going to get the molar mass. In this case, it's just HO, so that's going to be 1.008 grams per mole for the hydrogen and 16 grams per mole here for the oxygen, going to get us 17.01 grams per mole. So our percentage of hydrogen here in this case would be 1.008 grams per mole divided by 1701 times 100%, and that will get us give us 5.926%. And we'll do the same thing here with oxygen. In this case, just 1 oxygen, 16 grams per mole, 1701 grams per mole times 100%. And 16 divided by 17.01 times 100, 9406 oxygen. So we could clearly see in this case that is majority made up of oxygen. But more importantly, between the molecular formula, which was here, and the empirical formula, are the percent compositions the same or different? They are the same. And that's because obviously the empirical formula is based on the molecular formula. It's just the simplest ratio of what's present. So if you have the same ratio of masses, right, you could get the same percentages that are present. So you can calculate the percent composition between the molecular formula and empirical formula. They should come out the same. To 4 digits. Uh-huh. Yeah. Yeah, so in general, like we talked about a couple of things. In general, when you do pull the number off the periodic table, you typically go to 4 significant figures. And typically, in general, when you calculate the molar mass, 4 significant figures is typically what you would go to. And that's really the basis why we kind of rounded our percentages to 4 significant figures as well. Yeah. Yeah, so pretty much that's usually the amount of numbers that you should use on most cases when you're doing molar mass. Other questions? Okay. So we do see the percent composition, obviously, for each of these elements would be the same regardless of the molecular formula or empirical formula, because they're basically just ratios of each other, which means you have the same sort of proponent or composition of each. Any questions on that there? Okay, so we're going to continue on. So we've been talking about percent composition by mass, which is really lead us into empirical formulas and molecular formulas in terms of how to actually calculate them from experimental information. So I think we're at this example. So why don't you take a moment or two and work this example. We want the percent composition of hydrogen, phosphorus, and oxygen in phosphoric acid, which is H3PO4. I'm going to give you some numbers that might be helpful. Hydrogen 1.008, phosphorus 3007, 3097, and we got their oxygen 16. All right, so we're looking for the percent composition of each of these elements in this formula. So come up with what you got. Okay, let's take a look. So just like we talked about last time, in order to calculate the percent composition of each of the elements that are there, you got to start with the molar mass of the entire compound. Again, that comes from the periodic table. So that's going to be 3 times 1.008 for the hydrogen, plus 3097 for the phosphorus, plus 4 times 16 for the oxygen. That gives us a molar mass of the entire thing of 97.99 grams per mole. At this point, what we want to do is basically just take the mass of each of the elements there and divide it by the total. So the percent of hydrogen in this case would be 3 times 1.008 grams per mole divided by 97.99 times 100%. And that will get us looks like we'll go with 3.086% hydrogen. We'll do the same thing here for phosphorus. In this case, there's just one phosphorus, so that's 3097 up on top, divided by the molar mass of the entire thing. Again, times 100%. And that would get us 3097 divided by 97.99 times 100. 3161% by mass phosphorus. At this point, since oxygen is the last one, you could subtract by 100 and obviously add the other two together, and that would get you your missing percentage. Or you could just do the calculation 4 times 16 for our 4 oxygens divided by 97.99 times 100%. Gets us 65.31% oxygen in this case. Any questions on that there? And again, when you add up your percentages, they obviously should add up to 100%, which they obviously do. A little bit more, a little bit less, depending on rounding, but you should be definitely in the 100% mark there. Any questions on how to calculate percent composition by mass? So percent composition by mass is sort of an important sort of category, because when we go to calculate the empirical formula from experimental information, like we're going to talk about here right now, a lot of times you are given the composition of all the elements by its percent composition by mass. So there are several steps to calculate the empirical formula, which again is the simplest whole number ratio formula what's present when you have experimental information. So earlier we saw, if you are given the molecular formula, you can very simply calculate the empirical formula by reducing it down to a simplest whole number ratio. But when you're given more experimental information, there are a few steps that you have to follow to calculate the empirical formula. So let's talk about those steps to actually calculate the empirical formula here. So to calculate the empirical formula, the first thing you want to do is convert your percent composition into grams. So if you are given the percent composition of each element, you want to convert them into grams. And as we just talked about, the percent composition should add up to 100%. So a very easy way to convert your percentages into grams is to assume that you have 100 grams of everything. So a lot of times we will assume that we have 100 grams. And what that really does is basically just turn your percentages into grams. The numbers stay the same. You don't have to do any calculation other than basically turn your percentages into a gram. The next thing that you want to do is convert all your grams into moles. And as we've been talking about, it is the molar mass from the periodic table that we use to do that. So we're going to use the molar mass from the periodic table as a conversion factor to convert grams into moles. Now, once you do this, you will now have the moles of all the elements that are there. And what you then want to do is divide all the moles by the smallest number of moles. So for example, let's just say, for example, we had 4 moles of A after we converted it to moles, and we had 2 moles of B. And if these were the numbers that we got once we converted them into moles, what we would do is divide everybody here by 2 moles. And what that would give us for A is 2, and what that would give us for B would be 1. And if you do this and you actually get whole numbers like we just did there when we divide by the smallest number of moles, that would then be your empirical formula. So that would be your empirical formula if all are whole numbers. Or if they are not whole numbers, they're like really close to a whole number, like 2.999, you know, that's pretty much close enough to 3, or 3.02, that's pretty much close enough to 3. So in terms of rounding, you won't always get nice, perfect whole numbers. But if they are super close or just above the whole number, you could round. But they really do need to be really close to the whole number in order to round. Now, obviously, not all cases this will work out perfectly for you. So let's just say, for example, instead of 4 moles of A, we ended up with, when we calculated it, 3 moles of A. Moles of A, and we still had our 2 moles of B. Now, in this case, when we divide everybody by 2 moles, which is the smallest, and it's always the smallest you want to divide by, gives us 1 for B, but gives us 1.5 for A. And this would give us an empirical formula of A 1.5 and B 2. By the way, up here, this would give us an empirical formula of A2B, which would be our empirical formula. Now, we cannot have a 1.5. They do need to be whole numbers. So we do need to clear the decimal. This is considered too far to round. So 0.5 is too far to round up or down. You do have to find a way to clear it. And you could do that by just simple math. 1.5 times 1 is 1.5. 1.5 times 2 is, I believe, 3. And that is a whole number. So what you would do is you would actually multiply this entire thing by 2. So taking that guy and multiplying it by 2 would give us A3B4. And that would be our proper empirical formula, which is all whole numbers. So sometimes what happens when you go to divide by the smallest is you do not get a nice whole number, or you're too far away to round. And in that case, you need to find a common number to multiply the empirical formula by to get everybody to a whole number. As you can see here, we multiplied everybody by that common number, not just a guy that wasn't a whole number. Typical endings where it's considered kind of too far to round. If you end up with like a 0.33, like a 0.5, maybe like a 0.25, a 0.75, these are sort of considered too far to round. So really in rounding with empirical formulas, especially book type problems, not an actual experiment, but technically book type problems, it's got to be like pretty much on that whole number for you to be able to round, or very, very close to it. Again, if it's kind of above, like, 0.9 or less than 0.9-ish, or above 0.01 or 2 or 3, then, you're kind of getting into the area where you do need to find that number. Any questions on those steps? So these are the steps that you would follow to calculate the empirical formula based on information given to you. So let us look at one with real numbers here and sort of see how it goes. So we'll take a look at the example here together, which is here somewhere, maybe. There it is. We want to determine the empirical formula of vitamin C. It was found to be 40.92% carbon. Let's kind of write them up here so I get right a little bit higher. So 40.92% carbon by mass, 4.58% hydrogen, and 54.5% oxygen by mass. All right. So the first thing that we want to do is basically convert these percent compositions into grams. We also want to take a moment and just add up the percentages. Once again, they should add up to 100, which they do. If they did not add up to 100, you are missing something. So again, in this case, they do add up to 100. So what we could do is assume that we have 100 grams. And basically what that means is we have 40.92 grams of carbon. We have 4.58 grams of hydrogen and 54.5 grams of oxygen. So by assuming 100 grams, basically keeps the numbers the same, makes the math a little bit easier. The next thing that we want to do is convert all these guys into moles. So that's going to require us to go to the periodic table. And if we look on the periodic table, we see that carbon is 12.01 grams per mole. We see hydrogen from the periodic table is 1.008 grams per mole. And oxygen from the periodic table is 16 grams per mole. So using the molar mass from the periodic table, we're going to convert all these guys into moles. So that's going to give us 40.92 divided by 1201. Going to get us 3.4072 moles of carbon. 4.58 divided by 1.008. Going to give us 4.544 moles of hydrogen. And 54.5 divided by 16, going to give us 3.4063 moles of oxygen. Feel like I shorted a number there on the second one. I'll put it, we'll do the same numbers. 4.5437. 437. All right, any questions up to there? So it's really the same calculation we've been talking about, periodic table, grams to moles. At this point, we have the moles of each of the elements that are involved. We're going to divide everybody by the smallest number of moles, and in this case, it's pretty close, but it looks like oxygen here is the smallest number of moles. So what that means is we're going to take the 3.4072 moles of carbon and divide it by 3.4063 moles. We're going to take the 4.5437 moles of hydrogen and divide it by the same smallest number of moles. And we're going to take the 3.4063 moles of oxygen and divide it by the same number there. That is going to give us 1, obviously, for oxygen. This pretty much gives us 1 there for the carbon. And when we do our hydrogen, we end up with here 1.33. So once again, we chose the smallest number of moles, which is what you always want to choose, and we divided all the other moles by the same number. Any questions on that there? Now, this technically will give us our empirical formula, and if we look at it, it would be, at this case, C1, H 1.33, and O. Is that an okay empirical formula? It is not, because once again, they are not all whole numbers, and 1.33 is too far to round. So what we're going to do then is figure out a factor to multiply 1.33 by to get to a whole number. So if we multiply it by 1, we obviously get 1.33. We take 1.33 and times it by 2, that is 2.66. If I take 1.33 and times it by 3, that is 3.99, which is pretty close to 4. So in this particular case, we can actually multiply everybody not by 4, but by the factor of 3. So we want to multiply everybody in that formula by 3. And if we do that, we are going to get C3H4O3, and that is all whole numbers, and that would be our empirical formula in this case. Any questions on that? So once again, the steps are what you see here. Get it into grams, grams to moles, divide by the smallest. Again, if you hit whole numbers at that point, you're done. Put a box around it. If you do not, then you need to figure out a factor to multiply everybody by. Any questions on any of those steps there? Yeah. If 2 of them don't equal a whole number, what usually will happen in that case is you could find a common number that will fix them both. So usually because they're really all based off kind of the smallest ratio of each of them, you'll be able to usually fix multiples if they're not by the same sort of common number. Yeah. Other questions? All right, let's try one here yourself. Now that I did that one, let's do this one. Chemical analysis of a 1.078 gram sample contained 0.540 grams of sulfur and 0.538 grams of oxygen. What is the empirical formula? Sulfur is 3207 on the periodic table. Oxygen is 16. All right. So follow those steps, calculate the empirical formula here. Grams of sulfur, and we have the grams of oxygen. So we have 0.540 grams of sulfur. We have 0.538 grams of oxygen. By the way, if you add those numbers together, that is what this number represents, and you don't need that number in this calculation. It's just telling you that you're not missing anything, right? So once again, if you added those numbers up, and it didn't equal that 1.078 number, then you're missing some type of element mass or something like that, which you could get by subtracting from it. So in this case, we really are just going to take our grams of each of the elements which were given to us, and we would then convert them into moles. So using the periodic table, we would take our 0.540 grams of sulfur, a little 3207 grams per mole, and we'll take our 0.538 grams of oxygen, 16 grams per mole. Going to get us 0.50 divided by 3207, looks like 0.01684. And for the other one there, 0.538 divided by 16, 0.03363. And in this particular case, it is the moles of sulfur, which is the smallest number. So we're going to divide everybody by the moles of sulfur. So obviously for sulfur, if we take 0.01684 and divide it by 0.01684, that should equal 1. And if for the oxygen, we take 0.03363 moles of oxygen divided by 0.01684. That gives us 2 in this case, I believe. And that means we did hit whole numbers. So our empirical formula here would be SO2. Any questions on that one there? All right, let's try another one then, if there's no questions on that. Yep. Good. Yep. All right, let's try this one here. What is the empirical formula? We got 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. Once again, carbon 12.01, hydrogen 1.008, and oxygen 16. Okay, let's take a look at this. So once again, we are given everybody in percentages here. So we just quickly look at it. We do have about 100% there given, which means that we are good to just convert these guys into grams. So that would give us 49.3 grams of carbon. That would also give us 43.8 grams of oxygen and 6.9 grams of hydrogen. Once again, next thing we're going to do is use the molar mass from the periodic table and convert each of these into moles. So we'll do that. So that's going to be, again, 12.01 grams per mole of carbon, 16 grams per mole of oxygen, and 1.008 grams per mole of hydrogen. So converting those guys into moles gets us 49.3 divided by 12.01, 4.1049 moles of carbon, 43.8 divided by 16, 2.7375 moles of oxygen, and 6.9 divided by 1.008. 6.8452 moles of hydrogen. Any questions up to there? At this point, we're now going to divide by the smallest. So it does look like in this particular case, that is going to be our oxygen. So we're going to divide everybody there by oxygen's molar mass and get rid of some of this stuff out of my way, maybe. Oh, you get it. So we're here. I kept it, huh? All right. So we're going to divide by 2.7375, divide by 2.7375, and divide by 2.7375. So in the case of the top one should give us about, let's see here. Gonna give us 1.5. This guy here is obviously gonna give us 1, and 6.8452 divided by 2.7375 gonna give us 2.5. So in this case, we would have C 1.5, H 2.5, and O, which was sort of a question earlier. We do have a couple here that are not whole numbers, and again, are too far to round. So we could probably figure out just by looking at it that maybe if we multiply by 2, in this case would give us 3. And if we multiply this by 2, it would give us 5. So again, you could use the same sort of common number to fix both of them, which is in this case, you want to multiply this guy by 2. And that would give us C3H5O2. Once again, you do need to multiply everything by the 2 in order to get there. So as was the earlier question, again, that common number should take care of everybody if you have multiples that are not, again, whole numbers. Question on how to calculate the empirical formula here. All right, so once you try this, determine the empirical formula of this compound that's been found to have 24.75% potassium. It's all by itself up there on top, 34.77% Mn, and 51% oxygen. Let me give you some of these numbers that might be helpful. So potassium is 3910. Mn is I think it's 54, it's 94. Getting old, I can barely read that periodic table, but I think it says that, I hope. And oxygen is 16 here. Get the magnifying glass out, maybe. I don't know. I'll hold it farther. Okay, let's take a look and see. So here we are given, as we've been talking about, the percent composition by mass. You do want to, when you are given the percentages here, just quickly give it a look and make sure that they do add up to 100%. If by some chance they don't add up to 100%, then you're probably missing something, and you would have some information, obviously, to probably figure it out. But in this case, if we kind of look at it, we are shooting there about 100%, so we're not missing any elements. But you do want to make sure you always kind of look at that to make sure everything sort of adds up. With that being said, we're going to turn these into grams, which is really our first step, and we're just going to assume 100 grams. So that keeps basically the percentages the same numbers as the grams. So that means I have essentially 24.75 grams of potassium. I have 34.77 grams of Mn, and I got me 40.51 grams of oxygen. Now that we have them converted into grams, the next really major conversion is to take these grams into moles. So we'll use the molar mass from the periodic table to do so. So for our potassium, that's going to be 3910 on the bottom there, so that the grams cancel. We end up with moles. For our Mn, we'll do the same type of calculation here, 5494 grams on the bottom, mole up on top. And for our oxygen, would be 16 grams per mole. Again, all this comes from the periodic table, which is our molar mass of each of these. So taking 2475, dividing it by 3910, gonna get us a 0.63299 moles of potassium. 3477 divided by 5494 gets us 0.63287 moles of Mn. And lastly here, 40.51 divided by 16. Again, I'm not rounding too much here, so we don't, get a little bit of rounding error at the end or anything like that. Take it to a few extra digits, does not hurt in this case. So basically, we have our mass percent. We then convert it to moles. The next thing that we want to do is look at the moles, and we want to divide everybody by the smallest number of moles. In this particular case, it's kind of a toss-up, but it looks like the MN just barely edges out everybody else there for the smallest. So we're essentially going to divide everybody here by the 0.63287. 0.63287 and divide by 0.63287. When we do that for potassium, it gives us a 1. When we do it for Mn, it gives us a 1. And when we do it for our last guy there, it's going to give us basically a 4. 4.0006 looks like close enough for 4. That essentially hit us all whole numbers in this case, which means that is going to be our empirical formula. So this would be KMNO4, which clearly you will tell me that is what? That is potassium permanganate. Empirical formula, so either the empirical formula would be given to you, or you need to go through the process we just did in those couple of examples and calculate the empirical formula. Once you have the empirical formula, you also need the molar mass of the empirical formula. And lastly, you need the molar mass or the approximate molar mass of the actual compound that you're trying to figure out the molecular formula for. The good news is this guy right here is usually given to you. So usually somewhere in the problem, they'll say, hey, this thing has a molar mass of like approximately 95 grams per mole. They may also give you even a range of molar mass, like it ranges from somewhere between 90 and 100 in terms of its molar mass. Now, if they do give you a range of molar mass, you could actually choose anywhere in that range and it will pretty much come out the same. You could either choose the low end of the range, you could choose the high end of the range. Most people will probably shoot for something in the middle of the range. Yeah, so kind of use that for the calculation, but you could use the high, the low, or the middle, or anywhere in between when you do that. So what do you do with those two numbers? Basically, you take the approximate molar mass of the compound, which is given to you. You divide it by the empirical formula's molar mass, and it will give you a number. And that number is the number that you multiply the empirical formula by to get the molecular formula. So for example, let's say we had our empirical formula of our AB2. And let's just say that we did our calculation here and we ended up with a 4. Our molecular formula in this case would be A4B8. So we would take this 4 and multiply it, both things by it to get our molecular formula, which would be this guy in this case. Yeah. I will say that probably the only place where it's okay when you're doing these type of calculations to sort of round a little bit more freely than you would with the empirical formula is when you do this division here. So when you do this division, it may not always be a nice, pretty whole number, and it's probably okay to round that one because the molecular formula should be a larger number than the empirical formula, and they're related by whole numbers, right? So they're whole number multiples of each other. So you can pretty much round. So for example, if you did this and you got like a 6.1, you could probably call it 6. You got like a 4.3, you could probably call it 4. You don't really want to do that when you're doing the empirical formula calculation, but here when you're trying to figure out that multiple to multiply it by, because it should be a whole number. And because a lot of times what you're given in these problems is not the for sure molar mass, but it's like the approximate or experimentally found, there's a little bit of error in there. So it's okay to round a little bit more freely when you do this calculation as to opposed to when you do the empirical formulas calculation. Any questions on that there? Okay. So go and get after it here. Calculate the molecular formula here of this compound that is made up of 6.44 grams of boron and 1.803 grams of hydrogen. So boron, that looks like a 1081, I hope. So boron is 1081, and our hydrogen is 1.008. So you want the molecular formula here, which means you need empirical formula. Empirical formula is molar mass. and the approximate molar mass of the compound, which can be found usually in the problem. So see what you come up with here. Okay, let's take a look and see how you're doing. So in this case, we're looking for the molecular formula, and there's three things that we need. We need the empirical formula, which we are not given in this case. So we do have to go through our process to calculate the empirical formula. Once we do that, we will get the second thing that we really need, which is the molar mass of the empirical formula. So we kind of have to do those things together. The last thing that we need is the molar mass of the compound, which is actually given to us here. So approximately it is about 30 grams. So we're really just going to start out here with an empirical formula calculation. So it's already in grams, by the way, so don't ungram them. Yeah, so they're already in grams. Don't try to figure out percentages because you don't need to do that. So we already have our 6.444 grams of boron. We have our 1.803 grams of hydrogen. So once they're in grams, we want to convert them to moles. So we'll use the molar mass from the periodic table to do that. So for our boron, 1081, I think I wrote there, 1081 grams per mole. For our hydrogen, it would be 1.008 grams per mole. That's going to give us our moles of boron to be 6.444 divided by 1081, 0.59611 moles of boron. For our hydrogen, 1.803 divided by 1.008, going to get us 1.7887 moles of hydrogen. Any questions so far? So our next step in calculating the empirical formula is to divide by the smallest. So in this case, it looks like boron is the smallest. So we're going to divide everybody by the moles of boron. And that's going to give us a 1 there, bless you. And that's going to give us a 3, it looks like here. Once again, here we hit whole numbers. So that means that's going to be our empirical formula of BH3. It's our empirical formula. Any questions up to that point? So we now have our empirical formula. We have the molar mass of the compound. So the last missing piece that we need is the molar mass of the empirical formula, which obviously we can now calculate since we have it. And the molar mass of this guy would be 1081 for our boron, plus 3 times our hydrogens here. And that will give us an approximate, our molar mass for our empirical formula of, and we'll call it 1383 grams per mole. So now we have the molar mass of our empirical formula. The last thing we're going to do is take the molar mass that was given to us in the problem, the approximate molar mass. We're going to divide it by the molar mass of the empirical formula. And we're not going to times it by 100, just going to divide them. And 30 divided by 1383. And here we get 2.169. So again, as I mentioned, in this case, because it's definitely an approximate sort of molar mass, it is okay to round it basically here to 2 in this case. And that would get us a empirical formula B2H6. So really this one should be a whole number sort of ratio of the empirical formula, but because that molar mass is approximate, not maybe exact, and like I said, you could even get a range of it's somewhere in this range. You can do a little bit more rounding than normal. Any questions on that? This obviously would be our molecular formula here. Questions? Yeah.
They didn't get it wrong.
Yeah.
You end up with
I would say, yeah, if you screwed up the experiment, that's probably a good chance that you won't get a correct empirical. Well, obviously, if you were to do it to figure out something for like what is the empirical formula, you would obviously do it more than once, probably, right? You would do multiple trials and stuff like that. So hopefully you wouldn't screw it up. Hopefully it wouldn't be as precise and screw it up every single time the same way. But ideally, that's why we in experiments, right? We do multiple trials to see if we get the same results, right? Or if it's consistently the same, right? And that's that precision and sort of we're looking at. If you do this experiment like, 100 times, 20 times, whatever it is, and you get the same number every time, there's probably a fairly good chance that that is the right number, right? If you do it like 20 times and you get like 15 different answers, there's a good chance that probably you're screwing up somewhere along the way. And you know that probably the numbers you're getting, maybe one of them might be right, but you're not really sure which one it is. So that's again why in experiments, obviously we do multiple trials to know, okay, we keep still hitting this number. So, and we're doing everything hopefully correctly, that's probably the correct number. Yeah. Other questions? All right, so let's take a look at one more here to finish it up, I think. Phosphorus oxide contains 43.64% phosphorus, 36% oxygen. It was experimentally found to have a molar mass of 283.89. What is the empirical and molecular formula here? So phosphorus is 3097, I believe. And oxygen is 16. All right, give it a go. See what you come up with there. Here we're looking for both the empirical formula and the molecular formula. So obviously we do need the empirical formula to get to the molecular formula. We also have the other piece of information that we need for the molecular formula, which is the apparent molar mass or the molar mass of the compounds, 283.89 grams. So really here, we're going to start with just the empirical formula part of the calculation. We're given the percentages of each of these elements. Quickly looking at it, we got like 56 and 44. So that's around 100%. So we're not missing any elements or anything like that. We can again assume that we have 100 grams, which will basically again turn those into the same number. So 4364 grams of phosphorus and a little 5636 action there of oxygen. Now that we have them in grams, we're going to convert them into moles using the molar mass of each of these elements from the periodic table. And that's going to be a 3097, and for our oxygen, 16 grams per mole. That's going to give us for the phosphorus here, 4364 divided by 3097. We'll call it 1.4091 moles of phosphorus. For our oxygen, 5636 divided by 16 on our route here to our empirical formula, 225 moles of oxygen. We're going to divide by the smallest number of moles, which in this case looks like it is the phosphorus. So we'll divide everybody by the moles of the phosphorus. Again, we always divide by the smallest number of moles here. That's going to give us a 1 for the phosphorus. And in the case of the oxygen, not going to give us a 1. Going to give us basically a 2.5. So at this point, our empirical formula is PO 2.5. Can we leave it like that? We cannot. It does need to be a whole number here. So we kind of did this one earlier. Obviously, we took 2.5 times 1. We got 2.5. Well, 2.5 times 2 gets us 5. So that is going to be the factor that we want to multiply this empirical formula by. We're going to multiply this guy basically by 2. And that will give us P2O5 as our empirical formula. Any questions up to there? Yeah. Now that we have the empirical formula, we do need the molar mass of the empirical formula so that we can get to our molecular formula. So this is going to be 2 times the mass of phosphorus, 3097, plus 5 times the mass of oxygen. And that's going to give us 2 times 3097. That's not going to work. 2 times 3097 plus 5 times 16 looks like 141.94, 141.9 grams per mole. So we're going to take the molar mass that they gave us, that is for the compound, we're going to basically divide it by the molar mass here of our empirical formula. And in this case here, if you punch it in right, would probably help as well. Let's try that there, 141.9. Looks like a 2 in this case. So that 2, once again, is what we're going to multiply the empirical formula by, and that would give us P4O10 in this case as our molecular formula. Sometimes and rarely these days, but years ago in books, sometimes people will write the molecular formula like this and put the little 2 on the bottom. I'm personally not a fan of it. I'd rather just multiply it out and get the formula like that. But you might sometimes occasionally still see people write it like that. But I think you should probably multiply it out so that you do get the molecular formula. Any questions on that particular one? All right, so before we finish here, I do want to do this one and show you this problem. One other way that you could do this problem, that if you would like to do it the other way, you could do it. So let me just show you sort of an alternative way that you could have solved this problem and end up probably with the same answer. And then we'll talk about everything else and wrap it up here. All right, so the alternative approach, and I'll just leave our final answers here on the right, and I'll do it over here on the left. Alternative approach in this case is we actually do have the percentages given to us of each of these elements, and we do know the actual molar mass of the molecular formula, right, or the compound itself. So we could actually start with getting the molecular formula first and then working to the empirical formula, which is sort of another approach that you could actually do on that. And that's because when we add up these percentages, they do add up to 100. So that means out of that 283, 43% of it or so is phosphorus grams, and 56% of it is oxygen grams. So if I take the phosphorus and turn my percentage into a decimal, 0.4364, which is taking the 43.64% and dividing by 100, basically, and I times it by the molar mass, which is 283.89 grams, that would tell me that I have 4364 times 283.89 grams, around 123 I will call it 890 grams of phosphorus. I could do the exact same thing here for my oxygen, convert that into a decimal, 0.5636 times the molar mass of the molecular formula or the actual compound. And that will tell me in terms of grams of oxygen in this case, out of that 283.89, I got about 160 grams of oxygen. Any questions on that so far? Now that I have the grams, I can actually use the molar mass of each of those elements to get the moles. So we'll take the 123.890 grams of phosphorus. We'll divide it by the molar mass there of phosphorus, which is 30.97 grams per mole. So we'll take 123.89 divided by 30.97. That's going to hit me a 4 moles of phosphorus. I could also do the same thing here, 160 grams of oxygen divided by the molar mass of oxygen. And we take 160 divided by 16 gets us a 10 moles of oxygen. That is my molecular formula right there. And now that I have my molecular formula, all I have to do is, that is a 4 phosphorus to 10 oxygen ratio, which means I could divide everybody by 2 and still have whole numbers. Gives me 2 phosphorus for every 5 oxygens. And now I have my empirical formula. So if you do have the percentages given to you and the molar mass of the compound, you could actually start by getting the molecular formula and then simply reduce it down to the simplest whole numbers, and you'll have your empirical formulas. Or you could do it the other way, whichever way you like. They both come out the same. Obviously, you could not do that on some of the previous problems because we didn't have the percentages right. and maybe we don't have the actual molar mass of the compound itself. But in this case, you could go that way if you prefer. Options, good, yes, I suppose. Any questions on how to calculate molecular formulas, empirical formulas, percent compositions? Everybody. I divide by 2 because this is the molecular formula, and the empirical formula is the simplest whole number ratio that's present. So basically, in the molecular formula, there's 4 phosphorus for every 10 oxygens. So the only way that we could reduce it down and still get whole numbers is divided by 2. If we divide by any other number, we won't get whole numbers. And the empirical formula always has to be the whole number ratio of the molecular formula. Other questions?
This is one from your notes. What is the molecular formula of a compound that's composed of 1.52 grams of nitrogen, 3.47 grams of oxygen, and has a molar mass between 90 and 95 grams? It's really 90 and 95 grams per mole. We're looking for the molecular formula and the molar mass of the compound to 4 significant figures. In this particular case, we're giving a range for the approximate molar mass of the compound. Anywhere between 90 to 95 grams per mole is our approximate molar mass of this compound. After we're done with the calculation, we'll be able to actually figure out what the correct molecular formula is and the correct molar mass for it, which is sometimes referred to as molecular mass. So a reminder again, to calculate the molecular formula, we need the empirical formula, which in this case we do not have, so we're going to have to calculate it. We need the molar mass of the empirical formula, which we also will have to calculate. And the third thing, the molar mass of the compound, which, as I circled there to the left, we already have in this case. So we got one of the 3 things we need to calculate the molecular formula. So the first thing we're going to do after I kind of fix my writing here, I think I went off the screen, so give me a second here, grab an eraser, maybe do a little bit of erasing here. There we go. Kind of put it all on the screen. It was close. It just fell off there at the end. 90 to 95 grams per mole is our approximate molar mass. All right, so turning back to the empirical formula here, we're going to calculate it by first taking our grams of each of these elements, which were given to us, 1.52 grams of nitrogen, using the molar mass from the periodic table, 14.01. We're going to convert that into moles. We're going to do the same thing here for oxygen. We have 3.47 grams of oxygen using the molar mass from the periodic table, which is 16 grams per mole. We will also obviously convert that into moles. So it looks like here, grab my calculator, we got a 1.52 divided by 1401, going to give us a number of 0.10849 moles of nitrogen. Also now dividing the oxygen, 3.47 divided by 16, going to get us 0.2168 moles of oxygen. In this case, we're now ready to divide by the smallest number of moles, and looking at it, it is the nitrogen that we want to divide by. So we're going to divide everybody here by the moles of nitrogen, 0.10849, and divide the oxygen by 0.10849. Actually, 99, I'm sorry, it looks like. We're going to get 1 there, and we're going to divide the other guy there, and we will end up with a 2, I believe. And that's going to be pretty much 1.999, which again is close enough to round here to 2. And I think I misspoke. It is 0.10849 we're dividing by. So because we really hit whole numbers here for both of them, and again, that 1.999 close enough to round, gives us an empirical formula for this compound of 1 nitrogen and 2 oxygens, are basically NO2 being our empirical formula. Now that we do have the empirical formula, what we want to do is the second thing that we need after we check that off our list is we need the molar mass here of the empirical formula. So we're going to go back to the periodic table. We're going to calculate our molar mass. So that's 1401 grams per mole for our nitrogen. That's going to be added to 2 times 16 grams per mole for each oxygen that's present. Going to give us a molar mass of this compound of, looks like 4601 grams per mole. And we can now check that off our list. We now have the molar mass for the empirical formula. We were given the molar mass of the compound in the problem. Again, in this case, it is a range, so you can choose anywhere in that range. So if you want to kind of go halfway between the two numbers, we could start doing it that way if you like. We could divide by 92.5 grams per mole. And again, that's right there kind of in the middle of the range in terms of the molar mass of the compound. So we take our 92.5 grams and divide it by the molar mass of the empirical formula, which is 4601 grams per mole. We will get basically a factor to multiply our empirical formula by of approximately, in this case, 2. It's 2.01. That obviously is close enough to round to 2. Now, let's say you didn't want to choose sort of halfway in the middle, but you want to maybe take the low end of the range. And the low end of the range would be 90 in this case. And you could do the same thing, take 90 grams per mole divided by 4601 grams per mole, going to give us a factor to multiply the empirical formula above 1.96. Once again, close enough to round in this case to also give us a factor of 2. You could also have chose the higher end of the range here. And if you chose that higher end of the range, you're looking at really 95 grams per mole. So let's just do it here while we got a little bit of space. So we'll squeeze it in here. 95 grams per mole divided by 4601 grams per mole also gets us a factor of 2.06, which once again is close enough to round it to. So you can see that regardless of where you chose, middle range of the molar mass, low end of the molar mass, or high end of the molar mass, we basically got the same factor. So when you have a range like this for the approximate molar mass of the compound, you could really just kind of choose any number in that range, do a little bit of rounding to the nearest whole number, you get the proper factor. So now that we do know that it is 2, we need to multiply the empirical formula by. That will give us our molecular formula, which is N2O4 in this case. So our empirical formula being NO2, our molecular formula being N2O4. And now that we obviously have the molecular formula, we can calculate the actual molecular mass or molar mass of this compound for N2O4. Again, we're going to the periodic table here. 2 times 1401 grams per mole for our nitrogen. 4 times 16 grams per mole for our oxygen. Going to give us a molar mass of our molecular formula of, let's see here, grabbing the calculator, punching it in, and we get something like 9202 grams per mole, which is 4 significant figures, which is what the problem looked for. So once again, you could calculate the empirical formula first. In this case, we then got the molar mass of the empirical formula, which is the second thing that you need. And the third thing is usually given to you, which is the molar mass of the compound. All right, well, I think that wraps up the last couple of examples that we had for Chapter 8. So I hope this was helpful. I'll see you on the next one. Have a good one. Bye-bye.